Figure 1 shows SEM micrograph of single sample nickel zinc ferrite nanocrystal compact sintered at A, which is 500 degrees Celsius, B 600 degrees Celsius, C 700 degrees Celsius, D 800 degrees Celsius, E 900 degrees Celsius, F 1000 degrees Celsius, G 1100 degrees Celsius, H 1200 degrees Celsius, I 1300 degrees Celsius, and J 1400 degrees Celsius. From figure 1A to C, we could observe the arrangement of the grains within this temperature range, which are from 500 degrees Celsius until 700 degrees Celsius. The thermal energy supply was just enough to allow diffusion. During the diffusion and transition, the surface transport process also produced smoothing of the grain surface. The smooth surface of grains can be observed in figure 1D. During the intermediate stage, we could observe that the grains are now in contact with their nearest neighbors because the movement of the grains as a whole has stopped. This phenomenon can be seen in figure 1D and E. From figure 1E and F, they show clear significant changes of microstructure where a transition is speculated to occur at sintering temperature 900 to 1000 degrees Celsius, and it could be related to the size distributions. The grain size distribution showed the evaluation trend of grain growth. A significant starting grain growth of the sample can be observed in figure 1F for samples sintered at 1000 degrees Celsius, which correlated to the number of large enough grains with more than 0.3 micrometer. These grains contributed to better ordered magnetism due to better domain wall mobility. The porosity seems to linearly decrease with increasing sintering temperature. It is common in powder processing where the porosity during the sintering decreases by mass transport through lattice diffusion with grain growth. However, the samples sintered above 1000 degrees Celsius show a significant grain growth. Figure 1G until J show this phenomena. Above these sintering temperatures, the domain formation is favorable. However, at 1400 degrees Celsius, formation of more intragranular pores cause the porosity within the grains to increase. The pores will serve to pin domain wall movement. The increase in density, shrinkage, and decrease of porosity imply that the grain centers move towards each other, thereby reducing the size of the compact sample and at the same time eliminating the pores.
By using EDX technique, we can analyze and characterize the ferrous ferric constituents of the prepared ferrofluid nanocomposite X, Fe2 or 3 with different ratio X, which is X between 0 and 1 from magnetite and hematite nanoparticles. Figure 2 shows the EDX analysis, which is carried out for a sample of X equals to 0.5. The spectrum contained two peaks, which were assigned to ferrum and oxygen. The major peaks are around 0.8, 6.3, and 6.8 kilo-electron-volt, which correspond to the binding energies of ferrum. It also confirmed that no other impurities have been identified. EDX atomic ratio results are listed in Table 1, confirming the percentage of existing component in the composite. The weight ratio of the elements in sample is close to the theoretical weight stoichiometry ratio, 75.01% of ferrum and 24.99% of oxygen, which is very close to the chemical composition of 0.5 Fe3O4. These data show that total ion concentration in given ratio is close to the theoretical weight, and it is a summation of ion in both hematite and magnetite content of each nanocomposite.